software and different procedures and ideas for how we might explore other planets in the solar system when we start sending astronauts elsewhere. So we just have a couple slides here just to give you a little flavor about how this works. And Jim and I just spent the last week, we were each in one of these two rovers, and each of these rovers had two crew members in, and one of the crew members was a flight experienced astronaut, and one of the crew members was a field experienced geologist. And that's where Jim and I came in. So we each spent a week living inside that rover. And basically the only time that we came out of the rover was to go and walk around on what we call extravehicular activities, or EVAs. So that's an example of what the rovers look like. It's basically like a little camper for us. We live in there, we do everything in there, and it has the ability to really get us around to places that we wouldn't normally be able to get to look at the really good science. So I'm going to go through here and show just a few examples. Again, we're both geologists, and so I'm going to focus in on our ability to conduct geologic studies from the rover. So the rovers have 6 wheelbases, 12 total wheels, and they all have independent suspensions. So you can drive over some really crazy terrain that you wouldn't normally be able to drive over with just a regular car. And we call these the space exploration vehicles. And so on the top picture there you can see one of the space exploration vehicles right up here, and the other one is just trailing off behind it. So here's our pointer, and these hatches on the side are where you can go in and out and dock with other rovers, or you can come out the back side in this, what we call a suit ports. And it's a way that we can keep our suits and the dust that might stick to the suits outside of the rover. So in Apollo, the astronauts had a lot of problem with getting dust inside their lander, and it was irritating to them. So basically, we drive around in this space exploration vehicle, and this gives us the capability of driving over terrain that would be difficult to maneuver across, and then when we get to sites that are very interesting, we can leave the rover through those suit ports and walk around. So here's one of us out on an extravehicular activity after we left the rover. And so again, the big point here is that the vehicle can get us to really interesting places that we might otherwise not have access to. So just a little bit about what it's like in the rover. Again, we drive around from interesting site to interesting site, and as soon as we park the rover, we go ahead and we start taking pictures with some of the cameras that are loaded on the masts and around the outside of the vehicle. So here's an example. We had just arrived to a station, and so I'm sitting in the cockpit seat while my crewmate was getting our gear ready to go outside, and I'm initiating several images to be taken from outside of the local terrain. And then once we have taken several images that we can send back to a science room, a group of scientists that help us would be back here on the Earth, or here in Flagstaff, they're at our base camp. Then we go into the back of the rover and we don all of our gear, put on all of our hardware that we're going to take out with us on the extravehicular activity. So then once you're outside the rover, you're basically able to conduct geology the way anybody would conduct geology. So here on the left is a picture showing Jim and I on an EVA, and we're discussing what are the best rocks for us to sample. And you can see our backpacks are equipped with cameras, and that we also have a series of tools. So we have a hammer, a shovel, a drive tube, and sample bags, so that we can find the rocks that are the most interesting, or that we as field geologists feel are the most interesting, break them apart with the hammer, pick them up with the shovel, put them into the sample bags, and then we're able to return those to the Earth or study them on labs that might be on the planet that we're exploring. And here's just an example for you to see how we communicate with the science backroom. On the top right here is a picture of me looking at a sample. So we had just collected a sample, and I'm holding that sample up so that I can take a picture of it with this camera here that's mounted on my suit. So I'm holding the rock up, and this down here is the picture that I took, and that's the view that the scientists back on Earth or back at the base camp get to see. So they can see the rock itself, they can see the sample bag that we want to put it in. In this case, the sample is 0200, and then we have a wrist cuff right here that's basically a scale bar and a color code. so that the scientists can calibrate what color the rock is, how large the rock is, how large crystals in the rock might be, and they can use that to help them understand what they're dealing with. And then this picture shows how we can also use those cameras to take context images. So here are several larger platy rocks on the surface that have ripple marks on them. And so as geologists, we look for features in the rocks that might help us understand how these surfaces formed. So on Earth, ripple marks form when you're in an environment with some water flowing around. And if you've ever been to the coast and you've seen some shallow water, you might have seen ripple marks underneath. But when you see those features preserved in rocks, you can interpret the environment that those rocks formed in. So again, we use the cameras that are mounted on our suits to provide these kind of context images and the images of the specific samples so that the science team that works with us is able to help us understand what we're seeing. And then I just want to conclude this brief chat here by saying the SEVs, the space exploration vehicles, they really help us reach places that we otherwise might not be able to get to. And this is something that will be very important if we're exploring the moon or Mars or any other place that NASA might decide to send us to. And this is just a good example, I think, right here, showing these two rovers rolling around some terrain that you probably wouldn't want to ever put a lander anywhere near because it's just so rough and tough terrain to land on. So you can land far away, and then you can drive the rovers over and conduct your research on the surface. So with that, I think we'll just go ahead and take any questions that anybody might have, and we're ready to go. And we'll talk about the geology, or if you just have basic questions about the habitability and living in the rover, we can handle that too.
Great, thank you, Jake. We're going to switch over to the next screen. And you'll see here, if you've got a question, type it there in the box that says Ask Questions here. And we'll make sure we get those passed on. I also just want to mention, in case you've come on just in the past few minutes or so, originally we had about an hour's time, but it looks like because of weather conditions up there, we'll have about a half hour. So it looks like we have about another 22 minutes or so left to go. So we got one person, a couple people type up their questions. There we go. So for a minute, Jake, have you ever been in an older spacesuit, and how does this one compare?
That's a really good question. I personally have never been in one of the old pressurized spacesuits. And last year we wore some mock spacesuits. They weren't pressurized, but they basically attempted to mimic what a suit might be like. And the reason you do that is because it's a lot harder to walk around and maneuver on terrain in those kind of suits. The pressurized suits are really hard on the astronauts, and I had a chance to talk with my astronaut partner in the rover a good bit about that. His name is Stan Love, and he did 2 spacewalks during his flight. And basically what he told me was that during those spacewalks, those suits really beat you up. They're really difficult. And if you think about it, you're constantly trying to move something that has pressure on the inside trying to escape. So things like a glove. Think about like a rubber glove. If you blow it up, the fingers go straight out. So anytime you want to grip something, you have to fight that pressure constantly. So that really fatigues your hand and butchers up your hand and makes it difficult to work, and it can make you really sore. So that's one of the things that's very advantageous about this new design, the space exploration vehicle. You go out the suit port and you do your work in your spacesuit for a short period of time, and then you get back in the rover and you can rest in a comfortable environment, like living in your house. Yeah, go ahead, Jim.
Yeah, during the Apollo program landing on the moon, several astronauts in the later Apollo missions, they're doing deep drilling into the lunar surface. They came back and they lost their fingernails fighting these gloves like Jake was just describing. So the spacesuit, it does definitely wear and tear on your body. And so I think you can see if your fingernails coming off by doing work, it can be pretty taxing on your system there. And we're always trying to get better suits for maximum flexibility to allow you to do your geologic work or what have you. So suits can be pretty tough on you.
We see the next question. What what type of creature comforts does the rover have in it? The rover is, it gives us both a sleep station, so we have these curtains that we can deploy at night, and we lay down a small bed, and it's just about the right size to fit our bodies. And so you basically have all your personal items hanging from a soft locker in the hatch area, that big door that you saw on the side on the pictures of the rover we showed in the beginning. So you have all your personal gear there, your clothes, any items you might have. For instance, I had my iPhone with me, so at night I could listen to music or look at pictures that I had stored on my phone or play any of the games I had on there. So you have the ability to plug in items like that. We also had laptop computers, so at night you could put in a DVD and watch a movie with your crewmate if you wanted to. And then we had a lot of dehydrated food. So we have hot water heater and we get cold water. So we heat up our food and we eat it like that. And but it's, there's some things that you don't have. We don't have a shower in there, so we use a lot of this waterless soap. So it's a interesting way to take a shower, and it's not quite as refreshing as a hot shower might be, but it gets the job done and it helps you stay clean. And when you're in there for a week or 2 weeks and you're outside working really hard, you can imagine you probably do need a shower at some point. But you have washcloths, and you can use the water from the hot water pump to wash yourself off. You have any thoughts, Jim?
Yeah, it's very, very comfortable in there. I'm almost 6'3", and I could stand up. Head didn't hit the ceiling. Because when I was laid down in the bed, my legs weren't cramped or folded up. They could stretch all the way out, and there's even some room to turn on these little beds. So yeah, I agree. Jacob, it's very comfortable, and we had a great time in there.
So next question we see on here is, have you ever worked in such close quarters before, particularly in your field work? Well, sometimes when you're living out of a tent, you have several people in an extremely close quarters. So to me, this was actually much more comfortable than some of the conditions that I've done field work in. And my field partner, Stan Love again, astronaut, he had done field work in Antarctica. So he was used to having several people crammed into very small tents. So all in all, the rover is quite comfortable. And just like Jim said, it's a small area, but as long as you get along well with the person you're working with, and you divide your tasks evenly, and you can reduce frustration with each other by doing those types of things, it's really a very livable space. I consider it very nice. It was a fun time in there, and it's bittersweet getting done with your mission, because it's exciting, and it's something I always remember. Go ahead.
I agree with that. I mean, I didn't want to come out. I could easily, I think they could spend a month in there, and it was really an honor and a privilege being a crew member. And we had another great rover team we worked with, and all the people who support us. It was a great effort, and yeah, it's really bittersweet that it's over now. It went by so fast.
Yep. Okay, next question. What do you see as the biggest benefit from the mission for future lunar missions? Well, two of the big things that we were testing this year were how to operate in different communication scenarios. So for 3 days of our mission, we had constant communication with a science back room and a mission control center. So we had them to think about things like maintaining our timeline, making sure we were getting to the places we were supposed to go on time. So we were focused on the geology and navigating the terrain, and if we didn't know where we were on the timeline, we could just ask them, how much time do we have to get here? But on 2-a-day comms, which was the other scenario, we talked to them in the morning during a briefing, and then we basically had to get to a point in the evening at a certain time so that we could talk to them again. We didn't talk to them all day. So that was a little different. You had to manage your own timeline, and you had to make sure you were getting to where you needed to be on time, and that was a little more mentally taxing for us. But the work that we were doing, we've never done this before with 2 rovers, 2 crews at the same time. So we're dealing with those communication scenarios as well as the 2 different rovers at one time. And so basically what we were doing was learning on the fly, how do you do this? So everything that we did, we can assess it by having field observers and people in the back room, and we can see what works well and what doesn't work well. So right now, the week number 2 crews are in the rovers, and they'll go through similar scenarios, and they might do it completely different than us. And that's really what the team wants to see, is what does work and what doesn't work. And this is really going to be helpful for us in future missions because we'll have this base groundwork to depend on when we start building those kinds of missions. Jim?
Yeah, another way to think about it, I heard this analogy, so I can't take credit for it, but it's like when we have the communications with our mission control and science back room, it's like a football game and all your coaches are down the sidelines with you. But during the two-a-day comes, the coaches say, here's what you're supposed to do for the rest of the game, we're leaving, we'll see you when the game's over. So you're kind of on your own. And I thought that was a kind of a good example of the way to describe it, because you don't have that constant support there. So the coaches, not only the head coach, all the assistant coaches, and the people upstairs funneling down the plays and what you're doing wrong, what you're doing right. You're just on your own those 2 days. And I think both situations are very realistic for future lunar exploration or Mars or wherever we decide to go. And like Jake was saying, the reason we're out here is to test this stuff out and find the ways to do it that work real good and the ones that aren't so good and to discard those. And that's why we do these field tests, to iron out the kinks. So when we get ready to go, we kind of really ready to go and do it.
So the next question we see is, do these suits, being more short-term, have waste collection capability? And the suits have no waste collection capability for us. But one of the advantages to the way that the space exploration vehicle works is that we're not really outside all day like the Apollo astronauts were. When they went on EVA out of the lander, they were out there for upwards of 8 hours in the suit. So they had to have waste collection capabilities in the suit. The advantage to this is we're outside for a half an hour. The longest we did this during this mission was 2.5 hours. So you can, you kind of plan for that, and you go before you leave, and you go when you come back. But we did our bathroom duty back in the rover. Jim?
Yeah, I mean, that's the beauty of having this rover. You're home on wheels, and for a geologist, it's great because it means not like the Apollo guys had to go out and come back to the same place every day they went out there on the moon. They had a rover, but it wasn't pressurized. It wasn't nearly the size of luxury we have. So we have a great chance and a luxury to go out and explore and not have to come back to the same point every time. So we really maximize our territory we cover. And for doing geology especially, the more you see, the more you're going to learn. So it really is it's a great tool for geologists or the crews just to have in general.
And so the next question, how did the backgrounds and skills of the astronauts and field geologists complement and contrast? And that's a really good question. The crews are specifically chosen because what the team really wants is feedback on how do the science how do the operations from a space operations standpoint happen, and how do operations from science side of things happen. So in my rover, Stan, my astronaut partner, he did all the driving, he did most of the navigating. While he was doing that, I was able to look at the geology, make observations, collect data, and so we worked together to try to make sure that we were giving each other the ability to get our jobs done without stepping on each other's toes. And inside the rover, it's a pretty obvious division of labor at that point. And as Stan said, he felt that his primary job was to make sure that I was able to keep talking and to keep writing notes. So he tried to do everything he could to help me there. But the astronauts then have perspective on things that might or might not work from a space flight. So for instance, we were talking about your glove, in a pressurized glove, it's very difficult to grip things for long periods of time. So they give a lot of good feedback on tools and items that you might have to hold, because you want to build the tools in a way that you don't have to grip them constantly. So, Jim, your thoughts?
No, that's good. You give a good answer. I agree with everything Jake said, and I think the crews blended real well. Everybody recognized we're out there to have a successful mission, and well, I use a football analogy again, I guess because I like football so much, but it's like on a football team, everybody has a position, and they have to know what they need to do to execute the play and execute the football game to be successful. And so everybody has a role in this to play, and no one role is more important than the other. Everybody's pulling together as a team, and I think for me personally, I think the teamwork ethic part of it is really very, very, very exciting, and it's very rewarding to work as a team to pull these real complex operations off. So I think the space program is all about teamwork. You need all kind of experts in there. No one person can know it all. It's impossible. So that's really a rewarding part of it, like I said.
And so the next question, do you have to have a degree to become a doctor? And basically, yes, you have to go to school. And Jim and I both have a background as field geologists, so we have PhDs in geology. We both study different processes, but approaches that we use to study different processes include field work. So that's where our background comes into play. So the schooling that we have, we went through a university to get our PhD. Both of us have a PhD in geological sciences, and then that's what put us in a position to be selected for these crew slots on the desert rats. So if this is the kind of stuff you want to do, then you probably want to do that. But we also have a lot of engineers on here that most of them I don't think have their PhDs. A lot of them might have master's degrees. So it just depends what aspect of something like this you want to work on. We have a lot of interns here helping to support this work. There's a lot of people that work for NASA, but there's people who are working for universities, and there's people that are working for independent companies. So this is really a collaborative effort between NASA, academia, and other institutions around the country. Jim?
Well, I'd just say, if I can get a PhD, I think anybody can. I was lucky. I found something I was super interested in, and I think if you're interested in it, you'll be good at it. And to me, as a kid growing up, this is what I wanted to do. And it's really, it's just great to have a job. It's not even a job. I love going to work every day, because it's not like, oh, I gotta get up and go to work. It's like every day's different. It's just a great experience. So going through school and getting a PhD, it's basically a membership card to allow us to do a lot of this stuff. And like Jake said, there's all kind of different ways to be involved in this. As a PhD, a geologist, or other PhD scientists, an engineer. So it takes a team effort again. And if you have aspirations doing this kind of stuff, I would not give up on it and think, well, I'm not a straight A student, I can't work for NASA. It's impossible. No, it's not, because I can tell you for a fact, I was not a straight A student. When I got in grad school, my grades improved, but like I flunked algebra 2 in high school, for instance, and I had teachers tell me that I would never work for NASA, and I had a stubborn streak in me and didn't listen, and thank goodness had a lot of help, a lot of good teachers, and a lot of people support me. So you don't have to be a straight A Albert Einstein type person to work for NASA. If you are, it's not going to hurt, it's going to help. But I think that passion, determination goes a long way in a career.
Yeah, and just to reiterate some of those points, that what really makes this test work is that everybody puts in everything they've got. You give a full effort, and when you see things that need to be done, you do them. You don't ask. You don't wait for someone else to do it. You just work as a team, and you get it done, and you give everything you got, because it's dependent on. There just can't be weak links in the group, and that goes for the whole mission, but especially inside the rover. If you're in a small enclosed area with someone and they're starting to irritate you, you're going to start having trouble getting things done. So I mentioned several times the division of labor, and you really just have to pick your tasks. And some crews, they really have to talk about, you do this, you do that. With Stan and I, it just kind of settled straight out. We just both picked up our duties as we saw that we should be picking them up, and we never really had any problem. But it's all about just putting in a hard effort, and going to school is the same way. Just work hard, and if it's something you like and you're working hard, you'll get there.
It sounds like old-fashioned stuff you hear all your life, but it's true.
I'm gonna skip down here. Josh got a different question. Has the rover been on the dark side of the moon? And if yes, how does the dramatic temperature change affect the rover inside and out? I want to address the first part of that question, the dark side of the moon. Just a point I want to make here is that there really isn't a dark side of the moon. There's a far side of the moon that doesn't face the Earth, but it's not always dark. So we see the moon go through phases, and that's because the light from the sun is hitting different parts of the moon. So there is not actually a dark side of the moon that's always dark. We call it the far side of the moon. We don't see it. And to address the rest of the question, we have not put anything on the surface of the far side of the moon. It's first of all, we can't communicate with anything over there, but it's something in the future that if we had more satellites, like for instance right now we have the Lunar Reconnaissance Orbiter currently in orbit around the moon. If we have several spacecraft like that in orbit, then we might actually be able to communicate with things that are on the far side of the moon. But the real point here about the temperature change, that's something that we are dealing with now from a technology standpoint. it's quite a temperature change, several hundred degrees Fahrenheit if you're in darkness or in light on the surface of the moon. And right now we don't really have a great way to handle being in darkness on the moon. That's really cold temperatures, and it's hard for equipment to be able to handle those fluctuations in temperature. Some comments?
No, you did pretty good, Jake. I think one of the other things I'd say, and it wasn't really in your question, is that one of the other problems besides temperature, as you alluded to, is the radiation. You know, and also the dust. When you think dust, no big deal. It's like something you clean in your house and get rid of it. But the dust on the moon is a big deal. It can get into joints in your spacesuit, your electronics, short stuff out. It's really, can abrade your visor, make it so you can't see out of it very well. So there's dust on the moon, or be it asteroids or on Mars. Dust is a big problem, and you consider it a nuisance here. It really is a big nuisance we have to deal with, and we're still trying to develop clever ways to get around that. But there are a lot of issues in exploring other planetary bodies.
Okay, the next question that we have here is, how much training was required before going on this mission? And have you been on a mission similar to this before? Both Jim and I have worked with desert rats in the past, and again, there are a lot of different positions to be filled, even from a scientist standpoint. And most of the scientists that work with desert rats are working in a science back room. So they're at the base camp, but that's simulating being on Earth while a space mission would be operating. And they're the ones that really ingest the data that we collect, and they really try to understand the story behind it. So Jim has worked with that science back room several years in the past. I was a crew member on last year's test for a shorter duration of time. But the training that goes into it certainly takes some training. This year we spent 2 separate weeks down at Johnson Space Center learning how to drive the rover, learning how to operate all the instruments, just learning how to basically live in the rover, which is a little bit of a learning curve. But the real point I think that you're getting at here is how much training goes into a real mission. For Apollo, everyone considers Apollo to have been a very large success, and certainly from a mission operations and from a science standpoint it was. But from a science standpoint, all of those astronauts went through over 1,000 hours of geology training, basically in about a year and a half leading up to their mission. So they essentially earned a master's degree in geology in a year and a half, while they were also training just for the basic operations of the mission. So the training that goes into operating a mission, a real space mission, is phenomenal. And the training that goes into operating a mission like this, a field test on the ground, is also pretty hefty. So we do a lot of training, how to use everything, and you don't want to go out there and do things for the first time, because the data you want to get back for the team assumes that you know how to do this stuff. We're not trying to learn data on how you learn how to do this stuff. What we want are data on how do the operations work. Jim?
Yeah, I don't really have anything extra for that. Just another question. You did pretty good.
Okay. So Josh is clarifying on something he didn't want to know about getting a doctorate, but being a desert rat. So I think we kind of addressed that. I think there are a range of backgrounds here. We've got interns who are undergrads all the way up through people with PhDs. So all levels are here. There are a lot of engineers. There are a lot of scientists. It's really a collaborative effort between a lot of different people. What is the power source for the rover? This rover is electric. So whenever we would stop for a extravehicular activity, the support team that follows us. So what you don't see in some of these pictures is that we're followed by a pretty hefty support team. So there are Humvees out there with the engineers who built these rovers, making sure that things are still working, because these are not space flight ready vehicles. We're testing how they would operate, we're testing how you use the vehicles, but again, they're not field hardened to be ready for space flight. So those teams come along and they support us, and they keep things going. So they basically plug us in every time we stop, make sure we have enough power. You got any comments? Okay.
You did pretty good. So once again,
Is it harder to teach a geologist to function in a space environment, or to teach an astronaut what they need to know to optimize the geology mission outcome? That's a really good question, and you could probably ask 10 different people that question and get 10 different answers. It really just, it comes down to your background. The astronaut that I worked with, again, Stan Love, he actually has a science background. He's one of the scientists in the astronaut office. So it really wasn't a huge stretch for him to learn how to do what we were doing on this mission. Last year, I worked with astronaut Andy Thomas. He has an engineering background. So he was a little less willing to go out there and grab the rocks and make decisions on the rocks because he felt that he didn't know the lingo, the geology lingo. But once we got him into it, you know, we explained to him, don't worry about the words and terms that the geologists would use. Just describe what you see. When you get out, find what's typical, get a sample of that, and then find what's different and get samples of that. And when you pick them up, just describe what you see. The geologists in the science back room will take those words and they'll assign the lingo terms that we use in geology to your descriptions. So, you know, I think it's a learning curve for both the geologists and the astronauts, but it's difficult to say which one is easier done. For me, I'm a geologist, so it seems to me like it would be harder for me to learn what I don't know than to teach the people that I'm working with. But again, this year with Stan, it was pretty easy because he had a science background. Jim?
Yeah, the story I would tell was Jack Schmidt, who's the only geologist to walk on the moon on Apollo 17. I've talked to him, and he said many times that it's easier to train a geologist to be a jet pilot than to take a jet pilot and teach him to be a geologist. And so I think that's an interesting perspective coming from someone, really the only scientist to have gone to the moon, and he happened to be a geologist. So I think that gives you an idea. Geology is field geology learned by experience. And there's an old saying that the best geologist is the one that sees the most rocks. And you can't learn field geology in a book. You have to be out. You know, your laboratory is the Earth or Mars or nature, so to speak. So geology is one of these things. Field geology is an art and a skill.
Okay, the next question, what is the predicted range of the rovers on the moon or Mars? That's a really good question, and right now we, inside NASA and with colleagues outside NASA, those are questions that we're trying to answer. Engineers, you give them a number and they'll build something that will do that. So you could tell them 100 kilometers, 1,000 kilometers, or 5 kilometers. They'll make the equipment do that. They'll probably make it do better than that. But these are trade-offs that we have to deal with, because the farther you go, the more time you spend there, you have to pay for that somehow. And that there are a lot of trades that go into that. So we're doing a lot of studies right now trying to understand what kind of range do you need to have to answer big science questions on different planets. And that's different for a different place. So Mars and the moon might be completely different, and we might need different ranges for those planets. So that's something that there really isn't an answer for now, and it's a question that we have and we're trying to answer ourselves at this moment. But a lot of that just depends on the environment that we're working in. You have some thoughts?
Well, I don't know, if you ask the geologists, they're going to say as far as we can go, because the more you can get out there and see of the landscape and the rock formations, the more you're going to learn. So geologists would definitely want to push that envelope as far as you can feasibly do it. But like Jake was saying, there's some realities you have to deal with. Your consumables, your life support systems, what are your contingency and backup plans in case your primary life support system go out. You don't want to be too far away from help. So it's a lot of trade-offs you have to work back and forth.
Okay, next question. Did you use procedures books and checklists, or was the planning of tasks more informal? We had a lot of checklists and procedures, manuals, and you basically you have to have those. It's you can train as much as you want, and you can basically have it committed to memory, but things fall out of your brain really fast when you try to deal with all of it at one time, because you've got things going wrong in the rover, you're trying to get ready for an EVA. Once you get outside, you can be trying to collect rocks, but then you lose communication and you're trying to remember what the protocols are. How, for instance, on this mission, we had to at all times keep the rover in line of sight of at least one of us, and the two crew members had to be in line of sight of each other. So we could do things where one of us kept sight of the rover and the other person could go in a place where they couldn't see the rover, but they could see the other astronaut or their crew member. But you have to have those things, and there are a lot of things that you don't do frequently. Some things you do every day or every hour or every couple hours, and they become pretty easily committed to memory, and then you don't use the checklist as much. But some things you don't do as often, so you need those reminders. And some things, there were checklists, but we wrote our own checklists because we realized that those checklists just didn't cover the reality of what we had to deal with. So we made our own checklists and stuck them to the walls of the rover so we could remind ourselves how to operate. Jim?
Yeah, there are procedures, and if you don't think of it as directions for everything, ranging from how to prepare your food, to make sure the hot water pump is on, to go into the bathroom, to doing the high-level things like Jake's talking about, like performing your EVAs or your navigation between stations. So it's a constantly, you get checklists there, and like Jake said, some of the stuff you get ingrained into you, it's a second nature, just like breathing. But the other things, there's so much going on, it's nice to have it written down or little stickums on the wall or whatever to help refresh your memory. So it's a lot of that. I'd say the whole mission really revolves around that because it's, once again, the complexity of it.
Next question, are there any realistic plans for a living community on the lunar surface? These are things that are talked about, but again, at this point, especially with a mission like this, we're just trying to learn how to operate at all on another planet. And so for a mission like this, we're looking at how do 4 people operate in 2 rovers. So big questions like that, these field tests for desert rats don't really get into. There are a lot of discussions about that. What do we want to do when we send people elsewhere? Do we want to send just a few people to a lot of different places? Do we really want to focus on one place like the moon and build habitats and small, basically cities that we live in and operate out of? And there are very different approaches to exploring other planets. And so analog tests like desert rats, as well as many other analog tests that NASA runs, they get towards understanding some of these things, basic livability and operations and basically working in extreme environments and how do you live in small spaces with your crewmates. Those are the kind of questions that we're trying to tackle with these things.
Yeah, and right now there's a lot of decisions need to be made about where we're going to go and how many people and all these details. And you guys out there, if you get involved with this, will help make these decisions in the future. So I think it's a very promising field to get into if you're interested in that, and I'd highly encourage it because we're going to need a lot of workers, a lot of people to help do this stuff when we do it.
Next question, when do you think the rovers will be space ready? How long have they been in development? Well, these rovers have been in development for several years, I think 3 or 4 years, and they're working on the next generation rover right now. Again, this is the kind of question that you put towards an engineer. If you said, we need this to be space ready next year, I bet they could probably do it, but that's not the task they've been given right now. So what we're really working on now is just trying to understand the basic operability of these things and how do we use them. But again, part of the thing about, as a scientist, working with engineers on big tests like this is you give them feedback and you give them things to try to do, and they make it happen. I mean, they're top notch and they're really good at building that kind of equipment. Jim?
Yeah, just real quick is it's really fun being involved at the ground level, developing and help develop and test and design a new vehicle, and it's really once again it's an honor and privilege to have input into what this thing may look like, and hopefully it will go somewhere and explore. I think it will. I'm kind of optimistic. I don't know exactly where right now, but it's really going to be neat to kick back and think, hey, I helped work on that thing. Now it's up there on the moon or an asteroid or Mars, wherever it goes, and but the foundations and the hard work has to be laid out now, and so when decisions are made where we're going, we'll be ready to hit the ground running.
Next question, how do you get the majority of your funding? Well, both Jim and I, as scientists, our primary work is basic research. So a lot of our funding is to do the kind of research we do. So both of us do field work at different sites in the United States, and Jim works in Iceland as well. So that's where a lot of our funding comes from. Funding for things like desert rats, there are specific NASA programs that fund both the engineering side and the scientist participation side of this. So this is funded primarily through NASA. Some of the independent groups that are working here, they bring their own funding and get themselves here. But again, a lot of these are NASA missions and NASA goals that we're working on.
Yeah, it's good, Jake.
Right on. Do you get some of those famous space pens, the ones that you can write upside down for free? Yeah, funny thing about that is, you can spend a lot of money and effort to make a pen that writes upside down, or you can just write with a pencil. So, On a mission like this, it didn't really matter because we were still on the Earth and it was pretty easy. But we did not get any astronaut pens that write upside down. It's just not something we needed on this mission.
We did get to eat real astronaut food, though, that they're eating currently on the space station on the shuttle missions, and that was pretty cool.
Yeah, but it was really nice to go and get some pizza last night after we got out of the rovers. So a lot of freeze-dried food, and so it was nice to get out and get a warm shower and get a good night's sleep in a bed. Did you practice any emergency procedures during your mission, particularly during the times when you were outside of communication with the control center? We didn't do anything like that. One thing that we did do was at the end of our week-long mission, we brought our rovers back to something, basically a science lab, a habitat demonstration unit, or HDU. And this had been outfitted with some science capabilities, some analytical laboratory capabilities, as well as basic living capabilities. So there was a medical center in there was a general maintenance, a place where you could work on your suits, and basically just a bigger living environment that you could dock to. So we docked to that, I guess 2 days ago. Yesterday we spent all day working in there, analyzing some of the samples that we had collected. One of the things that we had to test was how well could minimally trained scientists and engineers handle the medical issues that they might have to deal with. So we had some fake laceration wounds that we had to stitch up and take care of, and I don't think either one of us would make a very good medical doctor, but yes, we did have to think about that, and the test in general did think about it. But yeah, Jim?
Well, I had to perform some simulator mock surgery on my commander, Chris Looper, and he looked at me and said, "You need to be a geologist, not a medical doctor."
Yeah, we work with rocks, not so well with the medical side of things. What is the average length of time for a mission from start to finish? Well, for a mission like Desert Rats, we've basically been operating nominally with 2-week missions. Last year there was a full 2-week mission, so 2 crew members, astronaut Mike Gernhardt and geologist Brent Gary, spent 14 full days in the rover. So we spent 7 days just now. They spent 14 days, and part of that test was just to prove that that could happen, that 2 people could live in a space like that for 14 days doing the kind of tasks that geologists would do. And so they actually focused a lot more on general maintenance type operations with the rover, whereas this year we focused heavily on just the science capabilities. But a big question is how long, if you were going to go to Mars, you wouldn't just go there for 3 days and come back. You wouldn't spend 6 months to go and 3 days on the ground and 8 or 10 months to get back here. You would want to spend a long time, and the moon is a wonderful place for us to try to test some of those things. Do you 7 days, 14 days, 30 days? At some point you become fatigued and your productivity will probably start to drop off. But there are ways to mitigate that. So the lab unit that we were in yesterday, that was a much larger living environment, and I think we all agreed that after probably 2-3 weeks in the rover, you might be getting a little stir crazy, but if you can dock with something like the HDU, you can spread out a little bit, stretch out, walk around without a big heavy backpack on, and that really, for me anyway, that would really increase my ability to handle longer duration. Jim?
Yeah, I mean, we're really in uncharted territory, because the only experience we had with humans on another surface of another planetary body is the Apollo program. Keep hearing about it, but that was a great program, and that got us to the moon. The longest time we stayed on the moon was only 3 days. 3 days. And so we're talking about going to Mars or going back to the moon and staying there for longer periods of time. A lot of this work is going to be critically important because we just don't really know how. And people say, well, we got the space station going. That's true. But life on board and science and operations on board the space station is totally different than exploring planetary surface in many respects. And most space station missions are typically 6 months. So we know the human body can take these things, and the record for a human being being continually in space is a Russian cosmonaut. It's like 437 days. So we know the body can take this, but it's different modes of operation and exploring, say going to the moon versus being in orbit around the Earth. So a lot of this stuff we're doing is laying the foundation for when we get ready to go wherever that may be.
Next question, can you give a specific example where the pre-planned checklists weren't sufficient and you made your own? There are some specific examples for that, and a lot of it just comes down to trying to get things into this mission at the last minute. But I think for me, where we made our own checklist was more where different aspects of the test overlapped. So different team leads, so people who built different things would give you a checklist on how to do their specific procedures. But when you're in the rover and you're integrating all these together in one big test, sometimes you have to be doing more than one checklist at one time. So a lot of what we did, at least in our rover, was we kind of built checklists that had components of several different checklists built into one big checklist. So when we would stop to go on an extravehicular activity, we would have to be doing science documentation at the same time that we were powering up our suits, getting everything ready for EVA. So there were a lot of steps that were kind of interfingered at the same time that you had to be doing. And if you just try to do one checklist, it would take a lot longer to complete a checklist and then start a new one than to work on both at the same time.
Yeah, not only doing extra.
Okay. But again, it just comes down to sometimes with those checklists, a lot of teams are really working hard right down to the wire to try to get their hardware in. And so sometimes you don't even have a checklist. So you have to, and that's why it's important to run these tests, because you really need to develop the way this stuff gets used. And another part that's really fun for this, at least for me, is the engineers come in and they've built this item that you're going to use, and they build it back at their office and in their lab, and then they come and they tell you, this is how you're going to use this thing. And then we use it a little bit and we say, no, that's not even close to how I'm going to use this thing. This is how I'm going to use this thing. And then they take that feedback and they improve the hardware. And that, for me, that's the really rewarding aspect to this, is your input goes into play right away, and the engineers, they listen to you and they make things better. And you can see that year to year as those improvements come around.
Yeah, one example I can think of is I was pretty rough on some of the tools. I kind of tore up some rock hammers out there banging so hard, and the guy who developed these tools was out there in the field several times with us in both crews, and he's taking notes and he's like, okay, I know what I need to do something to change this next time. For instance, the shovel was made of a little thinner metal, and I was doing some trenching and it got bent up out of shape, and he's like, okay. So he's taking notes. So that was kind of almost instantaneous. He's looking out there, seeing what we're doing, how we're using his tools, and seeing that some of the things he thinks he already has input from seeing us use them in the real situation to improve them for next year. And that was kind of fun working with him on that. And he's on the problem right now. And engineers are doing the same thing with the rover, like Jake was mentioning. These guys wanting to see it in a real test environment. You can do a lot of testing in a laboratory or a simulator rock garden. That's what they call it, landscape at Johnson Space Center. But until you get it out in real geology, you really don't know what's going to be great or what's going to not work good or only halfway work. So it's fun being part of, sort of in a weird way, seeing if we can break things. Not purpose, but in normal use of them to see if they're really going to hold up what they're supposed to.
Yeah, and that's a really good point. And the engineers will tell you, let's see if you can break it. So we want to know where it breaks down and why it breaks down under normal use. So yeah, that's the real fun part to this, is just working with these different teams and seeing things improve. Another question, with your support teams, how much maintenance did the crews actually have to perform on the vehicles? We actually had a really good run last week, and the rovers handled really well. We had some software issues that had to be worked from the outside, but I don't think there might have been one or two minor physical issues that had to be worked out, but the hardware performed really well for us, and that's great, because it really gives you a chance to get out there and see what happens over a full 7 days. And we really pushed it hard. We went over some rough terrain. This is by far the roughest terrain that we've driven these things on. And so we find out other things, like for instance our soft lockers, which basically have little wire straps to them that connect to the ceiling on rails. They hang there for us to keep all of our gear. Well, we've never consistently driven over such steep terrain as we did this year, and we learned that those lockers actually fall out of the rails that they're hanging in if you have the vehicle rolled to a side for a long period of time while you're driving. And that was something that just they didn't realize because they had never tested it that hard before. So that was some good feedback for the people who work on the interior of the rover. Did you run into any problems, and did all the hardware work as expected? That's basically the same answer. We ran into some problems, mostly software, I think, and these are really complicated machines to handle everything. But the ground crew's right there, and they get it working real fast, and we never really had any long lag times where we were just sitting around waiting for things to get fixed. How many teams work on the average project, and how many people can be on a team? Well, that's a question without a real simple answer. There are a lot, well, I guess there's maybe 4 or 5 really big teams here that build big pieces of hardware, like the rover team. But then there are a lot of smaller teams that just add aspects and components to those things. So the suit teams, they have the suits that build into the suit port on the rover. But then the suit teams have teams that add on to them. For instance, this year, the cameras we had on our suits, they had a wrist cuff that we used to operate the camera. Last year, we had to hold the rocks up and wait for the science backroom to take the pictures. This year, we had the capability of using this control mechanism on our wrist to take the pictures when we wanted to. So each year, you build and add with these little teams from different NASA centers. They add their components into the test and address the issues that you raised last year. So that was kind of a problem last year, was if your communications weren't working right, you didn't know if the backroom took a picture or if they had what had happened, and you didn't know how long you had to stand there and hold the rock in place and things like that. So this year, because we added this new wrist cuff, we were able to deal with that on our own.
Yeah, I'm trying to remember how many people are out here. I think it's 150 or something. I don't know, it's a lot of people.
Yeah,
it's a big effort, and there are other people who I'm sure have supported this and aren't out here necessarily in the field. So, and these tests get more and more complex every year. Different layers get added onto it, and you can see you really need to do this to start ramping up, preparing to when we decide the destination where we're going to go to do that. And I kind of said this earlier. I think Jake did too. It's like it's really pretty cool being involved at the initial stages of this, ground level, being a part of the testing and development and design. And I don't know. It's just I can think of no better thing to be doing right now. Only thing I can think better job than this would be to be an astronaut, and this is the next best thing to be in there. So I got no complaints.
Yep.
I want to interrupt. I got about 7 minutes.
Okay. And it looks like the weather is holding okay at the moment, so we'll probably be able to run through here at the end. Did you have limits on some activities to simulate the use of consumables? They tracked in great detail everything that we did. One of the things that's interesting is that inside the rover there are a series of cameras, so they basically watch everything that we do. Now we can turn those cameras off and cover them up, especially when we go to the bathroom, and usually at night we had them off. But otherwise, they really want to see what you do and how you use the rover. But every day they'd measure how much water they had to put into the rover for us, how much did we use. They measured all the waste that we took out of the rover. They measured the weight of everything that we took into the rover and then everything that we took out of the rover at the end of our mission. So we didn't really put limits on the consumables, but part of the test is measuring the consumables so that we have some estimate as to what we might have to deal with on a real mission.
Yeah, for one example, we had to keep track of everything we ate for breakfast, lunch, supper, and any snacks. And so like Jake said, they're really monitoring all this just to help for future, once again, future missions. You know, they're keeping track of, keeping tabs on pretty much everything.
Next question is, what is the most significant advancement in rover technology since the Apollo missions? Well, this is it. I mean, it's we haven't sent people anywhere else since Apollo. We went to the moon, several missions. We haven't sent people anywhere else except low Earth orbit. So we are developing the improvements on the rover, and the most obvious improvement is that these would be pressurized rovers. So the rovers that were used during Apollo, they were basically exposed to the lack of atmosphere of the moon. So they were open, no pressure. You had to be in your spacesuit all the time when you operated the rover. These rovers give you the comfort of living in a small area while you're in a comfortable environment.
And these are amazing vehicles these engineers teams have built, and I've seen them over the years in the field test, able to do things that the chase vehicles, SUVs, can't do. Four-wheel drive SUVs, like climb slopes to lava flows, go through sand dunes, You know, these SUVs are designed for off-road driving. Can't do it because Rover doesn't even blink an eye and goes ahead and does it. So it's an amazing vehicle, and I just, you know, it's a great job that these teams have done to put this thing together thus far, and it's very capable and very comfortable to live in, and just hope we get to see it, you know, go somewhere and really give it a chance to do what it can do its job, you know.
I'm going to jump down to a question down here. How many samples were you able to take, and do you know the total weight? I don't know the total weight, but I do know that we collected, I think, a little over 250 samples total. We basically, each crew, I think, had 3 extravehicular activities a day.
Yeah.
So we were probably picking up between 5 and 15 samples at any station. And so we collect a lot, and that's one of the reasons that we have the lab to attach ourselves to, because we pick all these rocks up, and then one thing we have to deal with is, well, can you bring them all back? Do you need to bring them all back? Because it costs a lot of money to launch things back to the Earth from other planets. So we have to be able to really make sure we're picking the right rocks and the right samples to bring home with us.
Yeah, we're looking forward to it. They're going to give us the numbers, the total weight. They haven't got that out ready to us yet, and so it'd be interesting to see what that is. But yeah, Jake said it really got up there pretty quick, and that was just for 1 week. You know, you can imagine if you're on another planetary surface, like from Mars, for instance, some of the surface stay times are up to 500 days. So you can imagine you almost bringing half the planet home, it seemed like. But that's important to do these studies to figure out, you know, how much can we bring back, and you can't bring back at all. So you got to figure out, well, this looks like that. We've already sampled that good enough. Let's just chuck it. And it's kind of hard to do because you got to basically go through like a high grading system, kind of like a way to check these things, grade them. This sample's better than that one, and that's the one thing we're trying to learn with this the PIM module that Jake's talked about, the GeoLab in it.
Yep, and I think we're going to have to tie it up now, and I just want to finish up by saying, speaking for myself, but I think Jim probably agrees, is we're both really proud and feel very honored to be able to participate with a team like this. And you know, it's like Jim said earlier, this is really fun stuff, and if it's the kind of thing that you're interested in, you know, just keep going for it. It's a lot of people out here and a lot of different roles to be filled to have a team that works well together, and you know, we really had a fun time as a crew on this test, but there's a lot of people that had to work really hard just to make any of this happen, and you know, I definitely consider it a privilege and an honor to work with such a good team.
Absolutely. I just say, you know, if you're interested in doing this, dream big and don't give up on your dreams. Follow them through, because it can take you to some amazing places.
Thanks a lot, Andy.
All right,
Thank you.
Thank you.
All right, thank you.
And Jim, we really appreciate the time out today, and thank you to all the folks behind the scenes there. Help make this happen. We really appreciate it.
Yeah, it was a little fight with the weather here at the end, but we got a good EPO team, PAO out here, so they really stuck in here with us and made sure we were able to get this done.
Excellent.
So thank you all for signing on and for your really great questions.
Have a good day.
And those of you who are still on, I know we were having some teachers possibly with us today. If you're a teacher and you have a classroom with you, I just sent my email to the Ask Questions box. If you could email me the number of students you had with you today, as well as the grade level, that would be great. We really appreciate having those numbers for our purposes. So again, if you're a teacher who joined us today, if you could email me your number of students you had there with you and grades, that would be awesome. And again, my email is right there in the questions box. So thank you again, everybody, for joining us today. This is really great, and we're really glad you could join us.